In this fourth video lecture, we will learn about the normal distribution, probability, type 1 and 2 errors, and tails. The normal distribution is foundational to our understanding of statistics in the social sciences. It is an observed phenomenon for a great variety of variables that include things like the amount of calories that a person eats in a day, the amount of hours of sleep a person gets at night, the level of depression a person might experience in a year. For all of these variables, the vast majority of people are going to score somewhere close to the middle, the average, the mean, with very few people scoring at the extreme ends known as outliers, away from the mean. So, for example, with calories, most people are going to cluster around the mean between, say, 2,000 to about 2,500 calories, with very few people reporting either very low calorie intake, so less than 500 calories for example, or very high calorie intake, say over 5,000 calories. Similarly for sleep, most people are going to report right around, say, 8 hours of sleep per night, going to cluster around that, with some people below, some people above that, but very few people at the extreme ends of that, at say 1 to 2 hours of sleep per night, or more than 16 hours of sleep per night. That reporting would be quite unusual. And the normal distribution helps us to understand how a person's score falls relative to other people in the population. For example, if we don't know the amount of sleep that a person gets per night, then a person's reporting of their sleep doesn't mean very much, because we don't know what the norm is for that, if you will. So understanding norms can be very useful, and that's how the normal distribution can help us. In addition, the normal distribution helps us to determine what's known as the probability of something happening by chance alone. And as we go through some of the parameters of the normal distribution, this will become clearer to you. Right in the middle of the normal distribution, if you look at the line that says standard deviations, you'll notice 0. 0 means the mean or the average. If you look at -1 standard deviations, so go back 1 standard deviations, between 0 and -1 standard deviations is 34.13% in that chunk. That means 34.13% of people are going to score or report about between 0 and 1 standard deviations from the mean. On the other side, between 0 and +1 standard deviations, again, about 34.13% of people are going to score or report between 0 and 1 +1 standard deviation from the mean. If you combine those together, -1 to +1 standard deviations, about 68% of people for most given variables in a population are going to score or report between around 68%, between -1 and +1 standard deviations from the mean. If you go 2 standard deviations out, so that's plus 13.59% on the left side to 34.13, and again 34.13 plus 13.59% on the right side, if you add those 4 chunks together, you get about 95% from those 4 chunks. That means 95% of people are going to score between -2 standard deviations from the mean to +2 standard deviations from the mean. In other words, only 5% of people are going to score below 2 standard deviations or above 2 standard deviations from the mean. This 5% is very important to statistics. Because of the probability that we've just discussed, it's very unlikely for a person to score -2 or +2 standard deviations from the mean. Only 5% of people do that. It's quite unlikely to happen. It's even more unlikely that a person is going to score -3 or +3 standard deviations from the mean. You would add another 2.14% to each side of the curve, so that gives you about 4%. So you add 95%, add 4% to that, you get about 99%, meaning only about 1% of people score below or above 3 standard deviations from the mean, meaning it is even more unlikely for a person to be reporting that kind of information. And that likelihood, the likelihood of someone scoring at the extreme ends of that curve, is how statistics can help us to determine whether or not something is clinically or statistically significant. And we're going to get into that more as we learn about the normal distribution. So, from looking at the bell curve, you should now understand that fundamentally the normal distribution is based on the mean and the standard deviation, and we get the percentages of people who fall either side from the mean and the standard deviation. You don't really need to know about percentiles or t-scores or Stanines at this point. Z-scores, just as an aside, is the same as standard deviations. If you look at the numbers, -1 z-score is the same as -1 standard deviation. What you really need to understand is standard deviation and mean, and the percentages that fall into those bins, those chunks, those portions of the curve based on standard deviations. So now that we've learned about the parameters of the normal curve, we're going to watch a video that helps us to understand the magic, the beauty that is the normal distribution. This is a wonderful video that helps explain and understand how the normal distribution occurs within a population. This was developed by a man named Francis Galton, who developed what's called the Galton Board. The Galton Board is a contraption that drops balls from the very top of the board, and the balls hit pegs as they fall down, and the balls can go either one side or the other side, left or right, for each of the pegs, and there is a probability of that occurring, and for each peg there's a probability of 50-50, for example, and that continues and continues until eventually the balls fall into those bins at the bottom, or you can call them columns if you want. You can see there the balls are dropping from the chute in the middle, hitting those pins or pegs, and clustering mostly in the middle, with some extreme scores but very few compared to in the middle. You can already see that most of the balls are falling somewhere in the middle there, although we don't have anything emulating the normal distribution yet in terms of the shape of the curve, and that's because of the sample size. We don't have enough balls yet. And that's part of the reason why we talk a lot about sample size in statistics, because if the sample size is too small, you don't really get a distribution that resembles the normal distribution or the bell curve. So the balls here are continuing to drop and hit pegs and fall down and continue to be collected within those bins. I think in just a moment we're about to see the extreme ends of the curve, and as you look towards the middle, just before we do that, you'll notice more clustering around the middle as more balls are dropped, and here we go, we see the right end of the curve. There's very few balls there, you can see at the more extreme end of that curve. As you look towards the left side of the curve, you'll notice again there are very few balls collected at the left side of the curve. Those are, by the way, known as the tails of the curve. The more extreme right and left ends are known as tails. So balls continue to drop. They're clustering mostly towards the middle. And they're starting to reach a point now where the balls are going to just stop falling in just a moment. And as we draw back, as the camera pans back, you will see that there are very few balls right at the extreme ends of the curve, and that the vast majority of balls there are in the middle of the curve. It represents almost magically very close to the bell curve, the normal distribution. And this phenomenon is found if this experiment would happen again and again and again. It's just the way in which probability occurs, that if you have a sample size that is large enough, the probability of getting the normal distribution is quite high. It's quite likely that you will get the normal distribution. And when you have a normal distribution, it's quite useful because it allows us to compare that sample with the population, since most populations follow the normal distribution. Magic. The theory is that all populations will fit this distribution if the sample size is large enough, and when this happens, it allows us to categorize people. Now, categorizing people isn't something that we particularly like to think about in the counseling field, but it can be quite useful for the purpose of not only doing research but also for assessment. For example, there is psychological instruments and inventories that are often used, things like the Minnesota Multiphasic Personality Inventory, or the MMPI, which helps us to differentiate between people with depression and people without depression. With the MMPI, there should be significant differences found between groups. In other words, that it would be unlikely by chance for someone who had depression to be in the wrong group. So, for example, to be in the non-depressed group. And if those groups were so well defined that those differences were unlikely to be found by chance alone, then if a person takes a psychological assessment, say the MMPI, and they have a score similar to the group of people with depression, it would place them in that group, if you will, that profile group, and help us as clinicians to determine whether or not someone is depressed. That's some real basics to psychometrics, and it has to do with the normal distribution. The normal distribution is also quite useful, again, not only to research, not only to assessment, but also for decision making. And at some point in your career, you may well be the director of a community mental health center or a school counseling program. And if you are the director of those programs, you often have to make difficult decisions about funding and how money is going to be allocated, what services are going to be provided, how you're going to meet the needs of all the people under your care. Often you are serving hundreds, if not thousands, of clients or students, and you have to make quite difficult decisions. And the way to do that is through data. One would hope that those decisions weren't being made just arbitrarily or without thought to what really is effective or what really is even cost effective. And the normal distribution helps us to do that because it gives us a degree of confidence. In other words, we know from the normal distribution when something is unlikely to be found by chance alone. So, for example, if we have a high likelihood of something being successful, if we have a high likelihood of something paying off for us, we're more likely to put confidence in going forward with that. You should also know about the normal distribution or the bell curve that there is a magic number, and the magic number begins at 30. 30 is the smallest possible sample size for a sample that starts to emulate the normal distribution. Now, this isn't going to be perfect when you have a sample size of 30. Part of the problem of that is that you will have outliers in the data that will dramatically affect the mean and standard deviation and the shape of the curve. The larger the sample size, the less impact you will have of outliers because most scores are going to cluster around the mean. So by the time you get to 100 participants, you start to get a sample that much better represents the normal distribution. And you typically in research studies want a sample size of about 100 people, ideally. 1,000 people would be much better and is going to really represent the population quite well if you have a sample size of 1,000, because it's going to very closely emulate the normal distribution. So we've just learned about the normal distribution. We're now going to learn about probability and error. Probability is very important to understand when we start to decide whether or not a study or finding is what's called statistically significant. And the way in which we decide that is based on the bell curve. If you look at the graphic in front of you, we have, if you recall, the average or the mean, and most of those scores are not surprising, but it would be surprising to have scores on either side of that, the 5%. So if 95% of people score within a particular range, it would be kind of unsurprising for a person to be scoring in that range, but it would be kind of unusual for a person to score in that 5% range, and that's what we look for, that probability of that happening just by chance alone. So the dirty secret to statistics is that it is wholly based on probabilities. Because there is always the possibility of error, findings are suspect to bias. Researchers therefore always have to accept some degree of possibility that their findings are false positives or false negatives. To determine results that are significantly different than what would be expected by chance or random error, researchers therefore agree on a predetermined level of risk known as a probability value. This p-value or probability value is usually predetermined at 5% risk of error. This is a predetermined amount of risk that researchers are willing to live with. If you recall standard deviations, 95% of people would score between -2 to +2 standard deviations, and that 5% outside of that is what we are willing to live with. So rather than say, well, we can live with, say, 32% risk, which is 1 standard deviation above and below, most researchers will say about 5% risk is okay if there's a possibility that my results aren't going to be accurate, or if I'm going to find something that doesn't really exist, or throw out something that really does exist, I want to have about 5% likelihood that that's going to happen, rather than 32%, which would be much too high, or 0.1%, which would be much too low, and we'll understand why that is in just a moment. So why 5% or 1%? If you recall, 2 standard deviations, if you look at the normal curve here, minus 1.96 plus 1.96, those are standard deviations or z-scores, same deal. Remember, about 95% of people are going to score within that light shaded area. In the dark shaded area, you only have about 5%. If you divide that by 2, you're about 2.5%, or in decimal, that is 0.025% for each side of the curve. So let's understand, now that you understand the numbers, let's understand what kinds of risks of error that you run when you conduct a study. Because hypothesis testing is really all about probability and the likelihood that our finding results really don't occur just by chance alone. Type 1 error, also known as a false positive, is when we set our acceptable error rate as too high. So this is when we have a probability value over 0.05 or 5%. And when we do this, we risk claiming that the independent variable has an effect on the dependent variable when there really is no effect and the null hypothesis is correct. So for example, if we had an error rate of say 10% and we said that CBT really did reduce depressive symptoms at a 10% error rate, we could very well be accepting a result that in fact would be found by chance alone, that isn't just occurring because outside of chance, if you will, that it really is happening. So that's too high of an error rate for us. But type 2 error or false negative is also if we set our acceptable error rate as too low. This is a probability or a p-value under 0.05 or 5% for a non-directional hypothesis. We'll talk about directional in a minute, non-directional. So if we set less than 5%, we risk claiming that the independent variable had no effect on the dependent variable, when in fact there really was an effect and the null hypothesis is not correct. So this would be if we said, well, 0.1%, I can live with that, a 0.1% likelihood of there being some kind of error or bias or confounding variable that really explains my results. And let's say that you found that CBT decreases depression, but not at 0.1% error rate. You would say, well, I can't justify my hypothesis now, and thus I must say that the null hypothesis is correct, when that may be just too stringent of a criteria and you're throwing out a perfectly good result. I have a kind of a fun example of this to play around with to help explain a bit more about type 1 and 2 error, to help understand how probabilities work. So in this example, let's say that you have a friend, a female friend, who has a birthday coming up, but you're not sure if that birthday is today or tomorrow. You have to make a decision about whether to tell that friend happy birthday or not, and there are probabilities of that you can live with and ones that you can't. So let's say that you make the decision to tell the person happy birthday and it is her birthday. Well, that's a good decision if you do that. However, if it is not her birthday, that's known as a type 1 error, a false positive if you will, because you've said it's her birthday, you've made that decision, but it isn't actually her birthday, you are incorrect. If you decide to say nothing and it is her birthday, that is a type 2 error or a false negative, because you decided not to say it was her birthday when in fact you should have said it was her birthday. If you say nothing and it's not her birthday, well, that's again a good decision, because you basically threw out the idea that it was her birthday and it was correct to do so because it wasn't her birthday. Now, when we make those decisions, especially in research, we want to make sure that we have some degree of confidence in the decisions that we are making. Usually that's about 95% degree of confidence. It's not okay in research to say, well, with about 50-50 confidence, 50%, I think that these findings would not have occurred by chance alone. That's not acceptable in research. Usually you have to have much more stringent criteria. In real life, you may well make that decision. Hey, 50-50, I'll tell her happy birthday and maybe I'll be right, maybe I'll be wrong. It doesn't work that way in research. You have to be quite confident in your results. Okay, so now we've explained type 1 and 2 errors, we're moving on to tails. Tails are also important to understand when we look at what are called directional and non-directional hypotheses. If we are unsure of whether the independent variable will cause the dependent variable to increase or decrease, we have a non-directional hypothesis. This is also called a two-tailed hypothesis because you're looking at both sides of the curve, both tails if you will, the left tail and the right tail. Now, typically we have a 5% criterion for a non-directional hypothesis because you're dividing up the tail by the curve by two tails. You're looking at the left side and the right side of the tail, and that's about 2.5% for each side of the tail if you're using 5% as your criterion, and less than 2.5% is really overly stringent. Certainly if you were picking 3 standard deviations, that would be only 0.5%, which is very, very low for a probability value. So most of the time you'll have 5% likelihood of risk when you have a non-directional hypothesis. Now you may well be asking yourself, well, what is a non-directional hypothesis? So let me give you an example. Let's say you're entering into a research project about happiness ratings between homeowners versus non-homeowners. Now, conventional wisdom would tell you that, well, you would imagine homeowners might be happier, but let's think about it for a second. If you're a homeowner, sure, you're building up towards some equity. Maybe you feel like you're able to live in a comfortable position in retirement, or maybe just enjoy owning your own home. But on the flip side, you also have a lot more bills to take care of. You also have a lot more upkeep. You may feel beholden to a house or unable to sell it if you wanted to move. And so all of these factors can play in, and so we may well say, based on all that, well, we don't know if homeowners are going to be more or less happy than non-homeowners. And if we say that, we have a non-directional hypothesis because we don't know if we're looking at just more happy, which would be the right side of the curve, or less happy, which would be the left side of the curve. So that's how a non-directional hypothesis works. I will say that in the social sciences it is quite unusual to find a non-directional hypothesis, and that's for ethical reasons. Going back to our CBT for depression example, it wouldn't really be ethical to say to a ethics board, for example, well, I'm thinking about a study. I don't know if my CBT is going to make people more depressed or less depressed. It could very well make them more depressed. Most ethics boards would frown upon that because you're essentially saying, hey, I may well harm people and make them worse off, but hey, it's all in the name of research, right? It's not going to look too good ethically. So most of the time research studies have a directional hypothesis, usually because they theorize things like CBT is going to reduce depressive symptoms. So we've just introduced directional hypotheses. If we want to know specifically whether the independent variable increases the dependent variable compared to random error, or decreases but not both increase and decrease, we have a directional hypothesis. So it's okay, for example, to say, well, I believe that my intervention is going to increase happiness or is going to decrease depression. So you can go either side of the curve, you just can't go both sides of the curve with a directional hypothesis because you're only really arguing that one thing is going to happen, not being open to either happening, increase or decrease. Directional hypotheses therefore use one-tailed tests of probability because you're just looking at the one side of the curve, the right side of the curve or the left side of the curve. In the graphic you see in front of you, you see the right side of the curve, and you can have either a 5% or you can actually have a 1% probability value or level, if you will, a level of acceptable risk. You can have 1% because you're only looking at one side of the curve. You're not chopping that into two and getting 0.5%. It's still quite low in my opinion, 1%, but you will see studies that use 1% as their criterion. 5% is much more typical, and that's what most people prefer to use. Just as an aside, if you ever read research articles that use less than 1%, they'll say P is less than 0.00001. That is usually considered to be data mining because usually you just set a level of acceptable error rate, and it really doesn't matter if it's less than 5%, just so long as it's less than 5%. You're not necessarily interested if it's 0.00001% likelihood of risk to occur, just as long as it's less than 5%. So anyway, I thought that I would share that with you because you will see articles that inflate their results like that. So we've just reached the review. We have learned about the normal distribution, probability, type 1 and 2 errors, and tails. This concludes this video lecture.